Everyone, thank you so much for coming to the area of Scala. Appreciate everyone supporting this event. And we really appreciate everyone coming out so we can continue to do this. Thanks, Iterables, for hosting us again. Really appreciate it. Did you guys want to have a message?
It's great to have you all here and keep the Scala flame burning. Yeah, Iterable, we're about 12 years old. We've used Scala the whole time. Our backend's fully Scala, market automation product. Charles, Greg, and I are here. We've been long time users of Scala since basically the beginning of Scala, and close to the beginning. I've been close to the beginning. Okay. But it's great to have you all here and also be in person. This is our own private meetup RTO.
No, thank you so much for hosting us. Really appreciate it. Well, our first speaker really doesn't need any introduction. I'm sure everyone knows Bill Venners, author of many of the great Scala books with Martin Orlowski, ScalaTest library, and I believe you're talking at this year's Scala Days conference as well.
Yeah, it'll be interesting to see.
So over to Bill, demystifying Scala 3 types.
Okay, thank you, and thanks for coming. How many people are using Scala 3? Okay, it's like a third, maybe. So, yeah, I just want to talk about Scala 3 types, and I think actually, since the AI is all the rage, I've been doing a lot of trying to get help with my friends, to write code for me, and I think types are going to be more important than they were before because it's how they type errors is good feedback for AI models as well as test failures, so it's relevant. Anyway, I'd like you guys to feel free to ask questions as we go because I'll keep it going because we have another speaker. So I'll be mindful. I'll be mindful of that too. Anyway, there's just I don't know if you can read this. If I can make it bigger without messing everything up. No. I'll tell you what it says. I was going to give you mental models to think about types. And one of them is I was going to compare the type level to the value level. I think that because most programmers are more familiar with the value level than the type level. There's new things in Scala 3, but they're all kind of have corresponding things at the value level. The other is reason with substitution. It's like lambda calculus, beta reduction. But I think it's a good way to think about it, to think about things, to understand. It's not how it's executed actually in the JVM, but it's sort of a mental model. And then thinking of types as sets because I think people are more familiar with set theory than type theory. I learned about sets first in grade school. So that's the 3 mental models. And I just wanted to start by kind of reminding, looking at functions, the value level. There's 2 kinds in Scala. There's the named kind and the anonymous kind. So the named kind, I say def, and then I give it a name. That's its name. And then I have the parameters. I'm required always to give the type. That's a type annotation. Then there's an optional result type annotation and an equal sign in the body. And the anonymous version of that, the way you can actually turn this into an anonymous function if you just get rid of the name and get rid of the def, and you start with the parameters. In an anonymous function, that's optional. You don't always have to have the type annotation, but you can put it there if you want. And then you cannot have in the anonymous function the result type annotation, right? So there's no way to do that. Then the equal sign just becomes this arrow, the rocket, and then you have the body. So that's 2 ways to do it. So in Scala 2, you could do this at the type level, but you couldn't do this at the type level, and you can now in Scala 3. So we'll get to that.
You could do a type ascription on the result.
Yes, that's my next one, type ascription. So this, because I can't, there's no way in the literal syntax to do a type annotation for the result type. What I can do is a type ascription. Anywhere in Scala, in any expression, you can just put a colon, and here's what I think the type is. And that's you, the programmer, telling the compiler, this is what I think it should be, and the compiler will check it. And if it isn't, then you'll get a type error. So here I put parens around this thing, and I said the whole thing is int-to-int. And this looks like a function, looks like one, but it isn't. This is a type. It's a function type, but it's not like something that computes an output int, from input int. That's this thing. That's actually a function. This is just syntax sugar because simply type lambda calculus used arrows, and so did Haskell, and so did Scala for the types. Because I have this type ascription here, I can actually leave off the type annotation, right? It'll infer it. And then I can also assign it to a val. And if I do that, then I can put that type, instead of an description, it's an annotation for the val. And again, I can leave off the parameter type of lambda. Okay. So that, I think, hopefully everybody's familiar with. All right. So I can always refactor a def to a val at the type level. All of this is true of, unless I say Scala 3, it's all true of Scala 2 and Scala 3, right? There are kind of two ways to do the same thing, because all I have to do to make this def a val is change def to val right there. And then I move the parameter list to the other side of the equal sign. So now I have the equal sign and then the parameter list. And I insert this little arrow, the rocket, and I put the body. So I've refactored a def to a val. So in the JVM, that's implemented, that's sort of implemented, or it's compiled to two different things that might have different performance. But if you pass in a string to either one of those, it will always give you the same result. So it's the same behavior as far as like not counting performance or how it's implemented.
But functional can be generic, vals cannot. So if you have a generic...
That's coming up too. Yeah, you're very good at foreshadowing. But that's in Scala 2, that's true.
Okay.
Scala 3, it's not.
Oh, cool.
Yeah.
Okay.
So that's a good point. But before I get to that, I want to talk about just what I mean by substitution. It's really how lambda calculus worked. It's not how the JVM works. But it's a good way to think about it, I think. So what I just took that method that was called capitalized def, and I just took off the def, but that's the same thing. So I want to just think about what happens with capitalized hello. I'm applying you apply the function to the data. I'm applying capitalized to hello, right? So the first thing you do is you just replace this whole shebang right here, this whole call, with the body, with this body where S is replaced by hello, right? So where here there's an S, so in there it's hello, here there's an S, there it's a hello. So basically I just replace the whole function call with the body of the function, and I substituted in the parameter, what was being passed for the variable. How would you put it? The argument for the parameter. It's probably a better way to say it. So that's step one. And step two is I'm just going to go kind of left to right to see what I can simplify. I can't simplify the if yet because hello.isEmpty isn't simple enough. It's not like as simple as I can make it. So I'm going to do that first. And I just change this guy, hello.isEmpty, to false. Whoops, false. There. So that's the only thing I changed. The rest is the same. But now I can simplify my if, because it's if false, so I can just change this whole shebang to the left-hand side, the else part. It's actually the right-hand side, the else part. So that's the else part. And then I can go, I'm going to start over here at the left, and I'll simplify hello.head to the little h character. And then I can simplify that .toUpper to the big H character. So I would look at that next, but this guy on the right-hand side is not simple enough yet, so I can actually evaluate that, and that's the string ELLO, right? And finally, I can take this whole expression here and simplify it to the result. So that's a way to think about it. It's not what happens in the JVM, but it's what happens in lambda calculus, and it gives you the same answer. So any questions about that? This is a way to think about it. Okay. So with currying is when I have multiple parameter lists, and so max def is going to find the maximum of x and y, but I actually have to pass them in separate parameter lists. So when you have a curried function defined like this, where the parameter lists are like that, you actually have to call it that way. And so the way you can think about this with substitution is first you do this one. So I'm going to take maxdef 1, and I'm going to apply maxdef to 1 and not mess with 2 yet. And what that's going to return is basically it's going to return the rest of this. But that's not a value. So it has to return a value. So I have to turn that into a lambda. So the lambda is going to take the y, and then you can't have this little colon int anymore because you can't have that in lambdas. And then a rocket symbol, and then the body. So that's what this first that's this guy. That's the first thing here. Oops. This guy without the extra parentheses. So that's after I just apply max f to 1. That's my result. But the one difference is x was 1, right? So I had, everywhere there was an x here, I changed it to 1. Here's another x, and I changed that to 1. Okay. I left the rest the same. The rest is the same. And so now I've got, a lambda. I've got, this is an application right here. And so I can simplify it by just applying it. So I apply this function to 2, and I plug in, basically get rid of this part. And everywhere y appeared, you put a 2, right? So that's this one. And then now I've got an if. I can't simplify that because this guy isn't true or false yet. So I just figure out what he is. He's false. Now that replaces with this. This I can now simplify to the else side, to 2. So again, I computed the max of 1 and 2 with substitution. Okay. So, and that's also not how it works. In the runtime, in the JVM, Scala compiles this down to a regular method that has 2 parameters. But you can, if I just say max def 1 in Scala, he'll make a lambda for you. All right. So the def I just stuck this in here just because it's kind of interesting looking. The def deval refactor you can do with currying methods too. You can always do it. And it's the same kind of process. I erase this guy, erase the name, and oh no, I'm sorry. This is curry def deval. I take def, I change it to val. That's the first thing. I change the name for the heck of it. These guys are the parameter lists. I have to put them on the other side of the equal sign. So they're on the other side. Here's the equal sign, and here's the parameter list. Look, it turned into that. And then the body is the same. You can't have the result type like this, but what I can do is put a type annotation on the entire val, and it's int to int to int, which I remember always being a little confused about, like, well, where do the parentheses go? Like, which one is which? It's always kind of goes like one parameter at a time. So I apply an int. So basically what this function int to int is, it means it's a lambda that takes an int and returns this guy, the guy that I highlighted. And it's the same thing with the literal. This whole body is a function that takes an int, the x, and gives back this function literal. And then at the
Lambdas are always one parameter functions.
Well, they don't have to be, no. In lambda calculus they are, in Haskell they are, but in Scala you could have more. In this example they aren't.
Gotcha.
But the thing I also thought was really nice about Scala is this looks the same. Like whether I'm using maxdef or maxval, it looks the same. In maxval, there's a dot apply happening behind the scenes, or 2 of them in that case. Same thing over here. I didn't mention it, but they look the same at the call site. It's just in this one, the compiler will insert a dot apply. That's a touch screen. I keep touching it. Anyway, okay. All right, here we go, polymorphic methods. So this is Scala, all this stuff Scala 2 and 3 so far. So an identity function is one that just returns the parameter, it takes parameter and returns it. And so if I made one for ints that took an int and just returned it, I can make one for string, took a string, just returned it. It can still like verbose and after a while. So why don't I make it generic? So that's what generics is for. And so I can define this identity def method with a square brackets a, and then I can pass in any type a and return it, and the result type is a also. So this is how I would invoke this, except I don't usually do this in Scala. Usually I'll leave this part out, and I let the compiler infer it. But the compiler does infer it. It actually sticks it in the tree, at that point, and figures out this is an int. So it's kind of like rewriting the code to this. So it's there conceptually, even if you leave it out. You can put it in there, and when you do, it looks kind of like a curried function call, like max def 1, 2, except this time the first one is square brackets, and it's a type parameter, not a value parameter. So what's neat about it is I can think about it using substitution the same way. And it kind of is sort of what happens in this case, because what I'm going to do first, just like I did max def 1 first, right? I'm going to say identity def int first. And what that's going to do is it's going to return the rest of this. But again, this is, I have to return a value, and that's not a value, so I have to turn this into a lambda that's going to take an A. But A is actually an int. I am substituting now. So it's going to take an int, and I won't have this part, but it'll return the int that's passed in, and that is this. So that's the first step, is I apply the first one, which is the type. I'm applying identity def to the type A at compile time. So that part happens at compile time. And I get back this guy, conceptually. I didn't mess with this, it's still the same. And so then I can now apply it. This is an int, 42 I can apply here. And, to do that, I get rid of this guy, and I just plug in 42 for every time we see x, and that's 42. So that's why I think the substitution model kind of helps people reason about, it can help you reason about like what's happening with type parameters. So any questions about that? Okay, so now getting to what was your name again?
Martin.
Just given what Martin said is you can't do that in Scala 2. You can't have, basically you could have polymorphic methods, like named functions, but you couldn't have polymorphic anonymous functions. So in Scala 3, they added that feature, and that's called polymorphic function literals. And these are actually values, and so they have types. There's also polymorphic function types. So that has a polymorphic function type. So this part, I'm going to just put my hand over this part right here. The stuff that I'm not covering is just a regular old function literal. So what they did is they allowed you to put a type parameter rocket in front of it. And so this always goes in square brackets. That's the type parameter. Let me get out of your way. That's the type parameter. And then there's a rocket, and you can have, one to many. And here you can have one to many value parameters. I don't know if you can have 0 there. It's possible. That probably would work. And then the body. Okay. And so what that kind of allows me to do is a def to val refactor that I couldn't do in Scala 2. So in Scala 3, I can make a val and assign it to this. This is a function literal, but it just has this extra type parameter at the beginning. And it kind of means the same thing, but as an anonymous function. So to the application looks the same, which is again nice. In Scala, that whether you're using an anonymous or named function, the application looks the same. I can leave this off and it will infer it, but usually we would not. So this one's actually a little more obvious to do substitution. I'm going to start by doing this one. This is always done at compile time. And what I'm going to do is apply identity val to int, and I'm going to get the right-hand side of it with a replaced by int. So it already looks like what it actually looks exactly like this. So I get x colon int rocket int, x, and then I can apply 42 and get 42. So that's how they work. A lot of us, yes.
Can the type parameter appear anywhere, or does it have to be at the beginning? Of
It has to be at the beginning. Can be more than one. But it's kind of true with methods too, right? They let us, it's a little bit arbitrary to me. In methods, it has to be here, and then you can have as many of these curried lists as you want, but you can't put another square one in there. But I think that would actually be more general.
Yeah, but if you want to benefit from curried functions, you kind of want to say, first the type, I bind the parameter, then later on I do B, and then something
You
else.
might actually be able to. Let's try that, because I wonder if I could do just add another one.
Yeah,
Let's
that was
see.
my question.
Let's say x, y colon b or something. And then I'll just return, you can't see b, y. Yeah, that worked. I don't know if you can see it. Is it useful, the thing here? So what, really that's, the reason that works is because this is, let's see, a polymorphic function value that takes a type and returns this guy. Like when you apply the first one, oh no, here it is. And when you apply the a, you get this back. That's actually a regular function value that takes an a, and what it returns is a polymorphic function value, which is a value. So that's why I could do it again.
Yeah.
What I don't think I can do is two a's in a row, like an a and a b. They probably won't let me.
So,
Oh, you did that.
Yeah, they don't like that.
Okay.
the reason that part of the reason Scala 2 didn't have this was probably because, that syntax basically gives a type of function and like function 1 bracket int comma and or something like that.
Yeah.
In Scala 3, what did they do?
It's called poly, and I forget what they really struggled with how to implement it.
I see.
And it's I think there was I forget now. But they have a way to implement it where there's an apply method. Essentially what you end up with is an apply method that has the type parameter in there.
I see. It's like trait poly 1 bracket.
Yeah, I
A,
can't quite remember
yeah,
exactly
fine.
how it's implemented. You can look it up,
Which is
but
how, I guess things how they emulated that in Scala 2.
probably.
Yeah, you could emulate that kind of stuff in Scala 2 by hand, but there was no direct support for it.
And I was going to say that like I used Scala for a long time, never needed this. So what's it good for? What I think it's really useful is when you're using hard-coded types. So when you like using functor or whatever, there's then it's actually a need for it. So I think if people aren't doing much of that, there wasn't much a need. But one of the things I remember Martin had said about his philosophy on design is regular. He likes Scala to be regular, which means there's no special cases. So I think this was an example of I can do the def deval refactor for non-polymorphic methods. So why can't I do it for polymorphic methods?
Yeah.
So Scala 3 has a lot of that. It really like got rid of all those exceptions. So anyway, that's this guy.
So in your example, a comma b should also work, right?
Yeah, a comma b should work. Yeah, that actually that's true. That's a good point. Let me
So it's
get
like
to the top.
the same
Maybe
as
small.
methods or functions.
What?
The same as in methods or
That's
functions.
right.
You can have multiple.
So let me do the a comma b one. That should work. I'm gonna put a space there for beauty. Yeah. So you got that. All right. So so I want to talk a little bit about sets. So I think actually type theory came from because set theory there was Russell found this paradox in it. This way it contradicted to itself, and later these other folks figured out a nicer set theory that got rid of the contradiction. But type theory was a way to get rid of it too, because the problem was the set of all sets that does not contain itself is a contradiction. So the way type theory gets around it is types don't contain themselves. So sets, like in set theory that we use these days, the only thing sets contain is other sets. That's how it works. Types contain inhabitants, which aren't types. So you can't have that problem of the types that the set of all sets that does not contain itself. So one way you can think of types is as sets of values, where like the inhabitants of sets or values. It's kind of touchy-feely, but that's sort of a way to think about it. So for example, type nothing has no inhabitants. There ain't no instance of nothing, so it's the empty set. So that's like that big empty set right there. Unit is a singleton set. It has only one element in it, or one member. Boolean has two, so it's either true or false. And like you can have the thing about set theory is if there's you put true in 20 times, it's just in there once, because anything that's equal is like the same thing, right, for sets. And then I made this little traffic like union, so I'd have one that's has three elements. Int has 2 to the 32, right? most types we use have like an unlimited number. There's like infinite cardinality set, but they're still sets. So then I wanted to talk about what subtype means. Using this example, there's a fruit trait, plum and apricot extend fruit, and then there's this pluot trait that extends plum and apricot. So it makes a little diamond, looks like this. Fruit. This is the type fruit. That's a plum and apricots are subtype of fruit, and pluot's a subtype of both plum and apricot. Pluot's is like a hybrid. So when you think of types as sets, subtypes become like subsets. And that's, I don't know, but when I was doing C++, we talked about derived types and base types. And then when I went to Java, it was subset and superset. And subtype and supertype. I think that's where it comes from, because it's the same kind of corresponding concept. So this is a Venn diagram from set theory. I've put a little fence around all the fruits, and these little circles are objects, instances of fruit. Everything inside this fence is an instance of a fruit. And then inside that fence, there's a plum fence, and everything inside the plum fence is a plum, which is also a fruit. And everything inside the other fence over here is an apricot, right? And then the intersection between plum and apricot, this little boat-shaped thing, that's like a fence around the pluots. So that this little symbol, less than colon, it kind of means less than or equals, because subtype is reflexive. Pluot is not just a subtype of apricot, it's also a subtype of itself. And that's what subset usually means, unless you say, like you mean exclusive subset, I forget what they call it. But to make it clear, they sometimes put that little line under there to say subset and including equal to itself. This set is usually thought of as a subset of itself. And the empty set is defined as a subset of everything else, just like nothing's a subtype of everything else. So anyway, that's kind of how to think about that. And then I think that can help you understand covariant result types, or like a way to kind of make them feel like they make sense. This is something Java has, and Scala has it. The example I showed here are vowels. So vowels they don't have a result type, they just have a type. But one way to think about a vowel is it's a constant function. It doesn't take any parameters, it always gives back the same constant value. And then when you compile vowels down, like member vowels, to the JVM, it's actually, it is that. It's a Java method. It doesn't take any parameters and always returns the same thing, which is why you can override them. So I override it down here, and I make the result type more specific. So in fruit basket, it returns the juiciest fruit. But down here, a plum basket is just going to have plums in it, or maybe it just likes plums. So its juiciest is going to be a plum. And then down here in pluot baskets, its juiciest is going to be a pluot. And sort of, what that means is that if I make a fruit basket, but behind the scenes I give it, I initialize it with a instance of a pluot basket. When I call juiciest, all I'm going to know is that it's a fruit, but what I'm always going to get is a pluot. And the reason that works is if you look at this guy, everything inside this fence is inside that fence, because set pluot is a subset of set fruit. So I drew this kind of sideways here, and that's why it's sort of like a way to think about covariant result types and why they always would be sound. So any questions about that one?
Just on the trait, should we also use override in the trait? Or
you don't have to when it's abstract. So these are abstract.
Yeah.
Just to fit on the slide, I didn't. I can't remember what I do. You don't have to. Scala lets you put override there or not. Okay. So that's covariant result types. Another thing that was new in Scala 3 was intersection and union types. And I just drew, like back here, I just drew this diamond, which is what you would think, well, it's what you had in Scala 2. That's what those 4 traits gives you, that diamond. In Scala 3, you actually get 2 extra types. You get the union type of plum and apricot, which is a super type. It's in between fruit and the plum and apricot, and you get the intersection type plum and apricot. I should say plum or apricot up here, which is below it. So the reason this was added is to make this the type lattice, which they called the type lattice in Scala 2, but it wasn't actually a mathematical lattice. And in Scala 3 it is. Because in a mathematical lattice, everything has to have a least upper bound and a greatest lower bound, every two types. And in Scala 2, there's a way you can put things together where the compute the least upper bound, it's an infinite series. You never get there. And the greatest lower bound, there was something like this intersection type in Scala 2, which got thrown out in Scala 3, which was like plum with apricot. It's similar, but plum with apricot is different than apricot with plum because linearization is different, and it was capturing that in the type. And so there's two of them down here. And it's a tie for greatest lower bound, so it doesn't have a greatest lower bound. Nothing did in Scala 2. So now the reason this works is because plum and apricot is the same, is equal to plum, apricot and plum. They're equal, so that's the type. It's just two for ways to write the same thing. But anyway, that was added, and what I put on here was, the above fruit is any ref and then any, and then below pluot is nothing. That's the entire above and below this guy. Okay, so now I want to propose a name for something, a kind. There is actually a different name for, like a different meaning for kind. But historically, I think traditionally, the type of a type was called a kind, and usually. And I think the type of the type in Scala is different than it is in Haskell. And so this is a better way to use that word is to talk about what the bounds mean for a type variable. So this guy right here is yet another identity function that's generic, just like the first one, identity def I showed you guys, except I did something, I changed, well, the type variable changed from A to T, but then I added these bounds here. So the other identity def I showed you had bounds, but they weren't explicitly given, so you get the default ones of the default lower bound is nothing, default upper bound is any. And here I set this greater than colon. It's kind of like you can think of it as greater than or equal to pluot, and then less than or equal to fruit. So let me show you that on the diagram here. Here's pluot. Greater than or equal to means you start here on any of these types. You can't go below that. The lower bound is something you can't go below. That's why it's the lower bound. And then fruit was greater than or equal to less than or equal to fruit, right? And fruit on the down. You can't go above it. It's the upper bound. Okay. And those two things essentially, they each form a set. So greater than or equal to pluot is all these types here. Pluot all the way up, and then any ref and any. And then less than or equal to fruit is all these types here, basically this circle, and nothing. So you get nothing in there. And so what the kind of that type variable is the intersection of its upper and lower bound sets. It's this guy. So it's everything between fruit and pluot, including those types. So the other thing people do to write sets is they put them in curly braces like that. So that is the kind of type variable T. Mm-hmm. It's the set of types that it could be. And the compiler will check it and make sure that it is one of those. Whenever you apply same fruit, you can apply it to any of those types, but nothing else. So it's very similar to a type, like if you have a value variable, x colon int, I can apply it to 42, but I can't apply it to hello. Here, t is a type variable, and it has a constraint also, which is a set of types. Instead of a set of values, it's a set of types. So that's like the very similar concept at the type level to the value level. Okay, any questions about that? Yes.
Silly question. So kind is a notion that you are introducing, or is that a?
It's a name.
It's a name that
it's a name because I was writing this down in the book, and I'm like, I really want to use kind for that. So I saw Martin in Poland at Scalar about 2 months ago. I said, can we use kind for this? And he said, yeah, that makes sense. So he may change his mind, and he's the final arbiter.
Okay.
The reason is that I think it would have been fine, except that we called something else a kind, higher kinded types.
Yeah.
That's the Haskell meaning of kind. So we'll see if it flies, but that's why I say I propose a name for it.
So there will be, and the full definition of kind would be what?
Oh, it's the basically the kind is defined by the bounds of a type variable. It's the constraint on a type variable.
Okay.
It's like the type of a type.
Technically, if you say like a type that a function type is a bound, then it's kind of the same. Yeah. This
It's
is kind of a subset of the higher kind of type kind, right?
well, I think higher kind of types is really talking about arity of type
Yeah.
lambdas.
Basically.
And so I like calling that arity of type lambdas because that's what it is. And I'll talk about type lambdas too in arity. So that's why the only thing that that's why I said it is I'm proposing to call this kind. And I'll see them again in next month. And I'll make sure that they're okay with this. Otherwise I'll rename it.
Isn't it just a bounded type parameter?
Well, every type parameter has bounds. It has a lower and upper bound. Every type variable.
Can you have more than one upper or lower bound?
No, each type parameter will just have one upper and one lower bound.
Can you have disjoint types as bounds? Like,
Yes.
So that would basically mean it is either one or the other.
No, if I could say, for example, I could do this. Let's see if it compiles. Let's flip them and say that basically it's an empty set. When you intersect these two. I think this is what you're asking. When you say disjoint, maybe that's not what you meant.
No, I meant like, could I set it as int and string?
Oh yeah, I can do that too. Let's do that because I didn't load in fluid. So I can say it's a subtype of int and a supertype of string, which is an empty set. And you can do that, although it may not do it if you're this explicit about it. Let's see if he complains. So he does let you, basically, even if he were to if the compiler would have not let you do this, there's things it can't catch. And the whole thing about Dotty is a proof that you never can get an instance of that. So this compiles, but what doesn't compile is I cannot call same root. I will never get an instance of type T because if I try to pass a string in, it's gonna not be. And so that whole proof thing they did was that it doesn't conform. So their whole proof was that even though they cannot prevent bad bounds, you won't be able to make an instance of it, so you will never have unsoundness. And that's the whole proof we were talking about before about the coq proof was about that. And they call it bad bounds. It's not really bad. It's just an empty set. Empty set is a valid set. You just don't have an instance of it. Anyway.
So one more question on the syntax. I have to start with a type variable t, right? I cannot do it like a fluid subtype of t, subtype of fruit or so.
No.
I cannot.
You have to have a type variable.
Yeah.
This is a
No,
constraint
I
on
cannot put the type variable in the middle. That was my
Oh
question.
no, you cannot. So here's what would have been another thing Martin could have done years ago. Instead of this, he could have said, what would look more mathy is this. It doesn't work.
That's what I meant.
This is how you do it in math, right?
Yeah, exactly.
Yep, doesn't work. So, whoops,
Can you
smiley
pass,
face.
can you pass
See,
null?
even the laptop likes the syntax, but no, that doesn't work.
Can you pass null to it?
Capital N null or? Oh, no. Okay, I hope not. I like his evil, he's trying to find a way to.
Null will be sub everything and super everything. No.
Yeah.
What about nothing?
Why does it think it's a string?
Yeah, but there's no value for nothing.
Can you,
There's no
can you
No, you can.
annotate it to
Yeah.
nothing?
Yeah.
3 question marks with a lazy.
Oh,
Can you annotate it to nothing?
Of course.
And null.
So that is not possible.
Null is capital N null.
But null is.
well, I know, he wants me to annotate with nothing.
Well,
No, but 3
Okay,
question
you
marks
can't
would
do
work.
that, but anyway, let's capital N null. Oh,
Three
no,
question
it's
marks.
capital
Nothing
N
is, no, nothing is a subtype.
null is not in between those bounds. It still
Yes.
doesn't work.
Yes.
What if you do 3 question marks?
3 questions.
The actual empty
You
set.
get the exception right
That's
away.
nothing, you're right. Well, I'll get the exception first, right?
Yes.
But it should compile.
Well, the type of
Ah,
benchmark.
Interesting.
even-
That's not compiled.
No,
Interesting.
because it's nothing. This is checking types, not values, right?
Yes.
So
That's
this
nothing
guy,
to sub
look
everything.
at this guy. The kind of T, it has to be between blue
Yes.
and fruit.
You have
Nothing
a
is not
lower
between
bound.
two out of fruit. Remember, it's actually not in the picture.
Yes.
It's left out.
Yes.
That's good.
Yes.
So what's kind of weird about it is like first they check the kind, and then they check the type of like something of that type.
Okay.
But anyway, okay. So that's kind. All right, this is like I looked in the spec of what they call these things. They could maybe come up with more user-friendly names. But there's monomorphic and polymorphic type members. So monomorphic type members don't have square brackets after them, and polymorphic ones do. But the way you can think about that is this is like a val at the type level, and polymorphic is like a def at the type level. Excuse me. So, and I just wanted to show you, I made 3 of them because you can have covariant result kinds for type members. That just is analogous to covariant result types for value members. And so what I did is the first kind here for my favorite in fruit lover, I have the kind, between fluid and fruit. And then I narrow it, I make it smaller. Under prunus is the a prunus is a kind of fruit that includes apricots and plums, so it's a generalization. I had to look it up. But like all of this stuff was in fruit lover. All of this is valid in the kind of favorite. But in prunus lover, I narrowed it to between the 2 intersection types. So the lower bound is the intersection type and the upper bound is the union type. So that means I severed this one. This is no longer good and this one's no longer good. But these 4 types are valid in that kind. And then I made it more specific. And then in the next one down, I actually made a type alias, which is an equal sign, which you can think of as making the type concrete. But it actually means this. It means that the upper bound and the lower bound are the same. And so the only thing that, when you intersect those 2 sets, the only thing that's in that set is apricot. It's a singleton set of types. So anyway, it's very similar to like doing that at the value level. But this is at the type level. And this is like that same diagram, but the difference is in the old diagram, show you the old diagram, the fences are types, right? And the little circles here, the elements are values. And this one, the fences are kinds, and the elements are rectangles that are types.
Mhm.
But it's the same concept. Okay. So what's nice about Scala is that anywhere he could do it, you get covariant results and you get contravariant parameters. Contravariant parameters I didn't show you or in these slides, but that's like in a subtype. I had one like if this guy took parameters. Actually, the next one doesn't need parameters. You can actually widen them, make them larger. So you can't do that on the JVM for like non-abstract types because they can interpret it as method overloading. So that's the one place in Scala it doesn't work. But everywhere else, you can actually get contravariant parameter types in Scala for regular methods if they're generic, because those all show up as object and the JVM, and he's like, he can actually do it, so he did it. So you get this stuff everywhere, except for where the JVM prevented it. Okay, so then polymorphic type members. Polymorphic is you don't have square brackets here. Polymorphic, you have square brackets. This is like a type level def. It's like a function I'm defining at the type level. It takes types as parameters and returns a type as a result. And you have to give each type a kind. There's a result kind and there's a parameter kind. So the parameter kind here for this guy, first of all, you say instead of def, you say type again. So we have def and val at the type at the value level, but at the type level, you just have type and type. It's always type. Just whether or not it has square brackets or not is how you decide if it's a monomorphic, polymorphic. So here's my, instead of like n:\, Anton Inker, I'm going to put it down here so you could see. Here's the name. This is the name of the abstract type I'm defining. Here's my parameter list in parentheses. There's the name of the parameter, and here's its constraint, which is a type. Here's the parameter list in square brackets at the type level. The name is v, and the kind is this, defined by this bounds. And then in an abstract type in Scala, you have to put the result type because you can't infer it. There's no body. So that goes there. And then an abstract type, you have to, basically everything has a result kind. If you leave it off, it's any, nothing to any. So here I actually get nothing as my lower bound because I didn't say it explicitly, and my upper bound is iterable of any. This is getting very contrived because I'm like trying to come up with an example where I can have map be the the more narrow one. So down here I just have one level where I say concrete fun extends abstract fun, and I override it. I could say override type there if I wanted to, but I leave it off because it's abstract above it. And I didn't change this one. So this is the one I could have widened. What you can do is just get erase greater than fluent less than fruit. Now it's greater than nothing, less than any. That will compile because that's contravariant parameter kinds. But anyway, I didn't do that. What I did is I made this a type alias. So a type alias, it just means that the left-hand side is another name for the right-hand side. So here, the left-hand side, if you say named of Fred, that means map string comma Fred. It's just another alias for it, another name for it. And it also, you could think of, instead of equals something, its lower bound is map of string comma v, upper bound is map of string comma v. So just the lower bound and the upper bound is the same. So that's the single set with just this type in it. So that is type level defs. So any questions about that? It's starting to look kind of vibraty, like hard to parse. But
so I understand
yes.
that for the subclass, the output needs to be iterable, and it needs to be within the bounds of iterable.
That's right.
But the argument can be widened. So
That's
my
right.
question is, what does work? Why can you widen the domain of a function?
Oh, that's contravariant.
Sorry.
That's the hardest thing to explain. Contravariant parameters. It is conceptually because if essentially the problem is, remember you kind of, if I create an instance of a concrete fun and I hold it from a variable of type abstract fun, all I know about it is that I can pass in something between a pluot and a fruit. So down here, if it's actually an instance of this guy, he can handle anything. He can handle that plus more. So it's about what he can consume.
You can do other code, and then if you find that it's within the upper bound of the parent function, you can try to call parent function.
Well, I think it's that basically it's this kind of example here. I may actually have it. This guy. So if this were a function, but it's this kind of thing where I create an instance of the subclass and I hold it from a variable, a reference of the superclass type. So what I know from this variable is that it's the superclass type. That's all I know. I don't know if it's a subclass type. So if you go back here, where's that one? This one. So I'm holding onto a reference of type abstract fun. I'm required to pass in a pluot to fruit. So that's the only thing I can pass in, pluot to fruit. And if the subtype can actually handle more than that, it's okay because he can handle pluot to fruit. That's the sort of why it works. It's kind of the dual to why covariant result types works. And Scala has contravariant parameter types everywhere except where Java won't let it because of overloading.
Bill, I don't mean to interrupt you, but a bit time check.
I know. I saw it was 7 o'clock. I'm almost done. Last thing is type lambdas. This is the another thing that was not in Scala 2 that was you could do at the value level, you'd have lambdas, but you couldn't do them at the type level. So the syntax of this is it looks like, here's a type parameter list, and then you have a different looking arrow with an extra angle bracket, and then you have a result type. So this is a type to type function, just like basically this thing. This is this one is a type to type function right here, but this is a named one, and this is the same thing, anonymous. So you can now do the def to val refactor, just like you could in Scala 2. I'm sorry, in Scala 3 you could do the def to val refactor, but at the type level. And this is the this is the application. They look the same, whether you're using the named one or the anonymous one. And this is where they ended up. So this is what happened in Scala 3 to the type lattice. The old one is over here in this cloud. So nothing got pulled down here, but there's a new type, a tip-top type called any kind. And all the type lambdas are sort of over here. And these are now called proper types. So, okay. So type lambdas are types, and you can use them as upper and lower bounds, and that's what happened to higher kind of types, actually, in Scala 3. So this is my last slide. Basically, I wanted to kind of point out that I think, what did somebody moan about?
No, that's amazing.
Yeah. So higher kind of types, you could always, in fact, I use it that way. Instead of using the old syntax, I use lower bound and upper bound of type lambdas. So what I've noticed about all these things, I think all these new features were driven by user requests, a lot of it from the type level folks, but so there were reasons for it, but what it does is it makes the language more regular. There's less special cases, and that was always his desire, like his aesthetic. There's a couple others that are like that, dependent function types, which I didn't talk about. This you always had at methods. Now you also have them in anonymous functions. So name functions, now you have them in anonymous functions. Context parameter resolution got more general. Context functions, methods could have context parameters, but not, or implicits in Scala 2, but not lambdas, but now they can. It came up with a very interesting way to do that. Not given was a way that made implicit lookup like full logic programming. And then the last thing is he actually didn't like people using logic programming in Scala implicit, so he added match types. And match types just means there's more. It's like Turing complete now. So I can actually compute types. I can probably compute any possible effectively calculable function in the type level now in Scala because of this guy. So anyway, that's all I have. So any final questions before we switch? Because we should switch. So, yes.
I have another question. Sorry, I want to yield to people who have not asked a question.
So what?
He wants to yield if somebody has a question. Somebody else.
Yeah, because I've asked a question before.
I would have a quick question.
Okay.
So does Turing completeness now mean I can send the Scala compiler into an endless loop?
Yeah.
Good feature.
Yeah. You'll notice after a while that it's not answering. Anybody else? You can answer yours. That's fine.
Okay, I'll go. So the other thing that I don't understand, like you showed diamond, right?
Yes.
Anything that has diamond can have conflict when the lower end wants to call a function that's shared by both their parents, right? So how does this diamond shape work with covariance?
Oh,
stuff?
I think that's a different subject. That is probably linearization.
Yes.
So you still
I didn't
still
talk
have
about
linearization.
linearization. Huh?
You still have linearization.
You still have linearization. You just don't have a type that says that the linearization is this direction anymore. So,
But you said that the join type don't care about the direction.
that's right. This just means you have both of them. You are an instance of both of these traits. It doesn't say which order they were mixed in.
So it's compiler implementation detail to say who goes first.
It's an implementation detail of your class that mixed these traits together, yeah. Which I like better, actually.
You can also explicitly resolve, if you have plum overriding something and apricot overriding, you can write super brackets and say, I want the implementation from plum, or I want.
Yeah, that's a secret feature. You probably should spread that around. You can do that. I didn't know that for a long time, but
it's in the programming in
I know,
Scala.
it's not a secret feature. Anyway, yeah. So that's all linearization, and it has really nice, elegant solutions for that. But that's but this did is just to make this was only two. It wasn't anything to do with that. This was just to make the type lattice an actual lattice.
Yes.
So, all right.
Great.